welcome you all in this course on mechatronics. Today we are going to discuss various types of sensors which are used for force and fluid flow measurement. Let us take first the force sensor. How do we actually measure the force? Okay. A very common used force sensor is the spring balance, which you often see available in the market as well as there in the many of our houses. Okay. Now, how does the spring balance measure the force? Basically, in case of spring balance, what happens is that the force is actually proportional to the displacement basically. Okay. So, here we essentially measure the displacement which is calibrated in terms of the force. Okay. So, forces are commonly measured by the measurement of displacement and force is proportional to the displacement. Okay. So, here by measuring the displacement we can measure the force. Then other type of force measurement device, very popular device is the strain gauges. Okay. And the popular form which is available is a strain gauge load cell basically. Okay. Now, you see that based on electrical resistance, strain gauge to monitor the strain produced in a member when stretched, compressed or bent by application of the force. Okay. So, in case of strain gauges basically the strain changes if the strain gauge is placed on a member, and if the strain changes. So, basically with the change of strain the resistance changes basically. Okay. So, that is how it is measured, and their arrangement is called load cell, and in a cylindrical tube usually the strain gauges are attached. Okay. So, you can see the attachment something like this. Say this is a cylindrical tube where forces can be applied, compressive forces can be applied, and here are the strain gauges which are put into in this particular fashion. Okay. Now, when forces are applied here, then what happens? Strain gauge gives a resistance change. Okay. And this resistance change is actually the measure of the applied force. Typically, such load cells are used for forces up to say 10 meganewton. Okay. As you can see here, and strain gauges which are based on the concept of the bending of an element. Okay, they can be also used to measure the smaller forces, say 0 to 5 Newton to say 0 to 50 kilonewton. So, in this range you can use the strain gauges which are put on a element which bends. Next, let us see the measurement of the fluid pressure. Now, basically fluid pressure is measured by elastic deformation of diaphragm, capsules or bellows or tubes. Okay. So, suppose you have a flat diaphragm like this. Now, when a pressure is applied, your diaphragm is going to deform basically. Okay. So, this is how what is the principle of the pressure measurement is, and to increase the sensitivity of the diaphragm, some corrugation is done, as you can see over here, and this is what we call it as the corrugated diaphragm. Okay. Now, there are essentially the three types of pressure measurement which we come across. One is the absolute one, that is where the pressure is measured with respect to vacuum. Then the differential one, where the pressure difference is measured, and the other one is the gauge one, where the pressure difference is measured with respect to the barometric pressure or the atmospheric pressure. Now, diaphragm movement here, as I said, that basically the pressure is measured by the movement of the diaphragm. Now, the question is, how do we measure the diaphragm movement? If we can measure the diaphragm movement, we can measure the pressure. So, the diaphragm movement can be monitored by strain gauges. Okay. So, suppose you have a pressure diaphragm pressure gauge is here, where pressure is supplied from this side, and here is the diaphragm, and the strain gauge is this element. Okay. Now, here the two strain gauges can be used in the radial direction, for example, this direction, and the two strain gauges can be used in the say your circumferential direction. Okay. So, total 4 strain gauges can be used over here, and these 4 strain gauges basically they are connected to form the 4 arms of the Wheatstone bridge basically. Okay. And there from Wheatstone bridge we can find out the change in the resistances, okay, or the voltages, whatever way you want to do it, you can do it. Now, an use of this type of device is in cars to monitor the inlet manifold pressure. Okay. And here a silicon diaphragm with the strain gauge as specifically doped areas of the diaphragm that is used. Now, capsules can be formed where you have basically the two corrugated diaphragm. Okay. So, you can see that one diaphragm at the top and another one is there. So, this type of combination is what is we call it as a capsule. Okay. So, they are just two corrugated diaphragm combined, and they give greater sensitivity. Okay. And when we stack up capsules are used, and they just is what is called as the bellows. So, stack up capsule is just a bellow, and they are even the more sensitive for the pressure measurement. Now, these bellows can be combined with LVDT, okay, to give pressure sensor with an electrical output. Okay. So, if we combine this bellow with LVDT, where you have the primary coil here, secondary coil here, and I can put a iron rod in this one attached with this bellow, and when the pressure is applied, there is a movement of the bellow, and in turn there is a movement of the LVDT movement of the iron rod, which is there in this LVDT. Okay. So, the diaphragm capsule and bellows here are made from material such as stainless steel, phosphor bronze and nickel, and rubber and nylon is also being used for some of the diaphragm, and they can measure a pressure up to say 10 to the power 3 to 10 to the power 8 Pascal. Now, you see a deformation is obtained using a tube with an electrical cross section. So, suppose if there is a tube with electrical cross section, now if you supply pressure, okay, then with increase in pressure what will happen, it will try to tend the take of the form of the circular capsule, okay, circular cross section. So, that is there. Now, such a tube in the form of C shape is what is called as the Bourdon gauge, which you must have studied in your school classes. Okay. So, here the C opens up basically to some extent when the pressure in the tube is increased. Now, we can also have a helical form of such a tube, and that gives the greater sensitivity, and these tubes can be made of stainless steel or phosphor bronze material, and they can measure a pressure up to 10 to power 3 to 10 to power 8 Pascal. Next, let us look at the piezoelectric sensor. Okay. So, piezoelectric sensor basically work on the principle of the piezoelectric, okay, and these are these devices used, piezoelectric sensors use piezoelectric material which are ionic crystals basically, and you see that when these crystals are stressed or compressed, there is a generation of electric charges with one phase becoming in the one phase you have accumulation of positive charges, and another phase you have accumulation of the negative charges. Okay. So, as a result a voltage is produced. Now, the net charge Q on the surface is proportional to the amount x by which the charges has been displaced, and since this displacement is proportional to applied force, we can write Q is equal to Kx, and this I can write another constant say S into F. So, basically here we can see that the Q is directly proportional to the F. Okay. So, that is there, and here this K is constant and S is a constant term that is called the charge sensitivity. Now, this charge sensitivity depends on actually the material concerned and the orientation of the crystal. So, the value of S is usually say 2.2 picocoulomb per Newton for the quartz when the crystal is cut in one particular direction and the forces applied in a specific direction. Now, these metal electrodes can be deposited on the opposite faces of the piezoelectric crystal, as you can see here. So, at the opposite faces of this piezoelectric crystal, I am putting the metal electrode over here. Okay, and then the capacitance of the piezoelectric material between these two plates can be given by epsilon 0 epsilon r A by T, where this epsilon r is the relative permittivity of the material, A is the area of these plates, and T is the thickness over here. So, basically what happens that by putting the metal electrode we are forming a piezoelectric capacitor. Okay. So, this the capacitance of this piezoelectric capacitor can be given by this expression. Now, I can write this C as charge per unit voltage. So, Q by V, and from here I can write the expression for V as I do the cross multiplication here. So, we have V is equal to Qt by epsilon 0 epsilon r A, and this Q I can now substitute as SF Okay. So what basically we see that if I put this S epsilon 0 epsilon r together, and I write this as SV, and my F by A is basically pressure and T. Okay. So here basically SV is the voltage sensitivity factor, and you can see P is the pressure. So what I want to say is that the voltage across the capacitor plate, that is going to be proportional to the pressure. Okay. So the voltage is proportional to the applied pressure. Okay. So this is how this pressure is basically measured with the help of this piezoelectric capacitor. Okay. So the voltage sensitivity for the quartz is about 0.055 voltmeter Pascal, and for barium titanium it is about say 0.011 voltage meter Pascal. Now, piezoelectric sensors are used for the measurement of pressure. I have already told. They can also be used for the measurement of forces as well as measurement of acceleration. Okay. The application have however to be such that charge produced by the pressure does not have much time to leak off basically, okay, and thus tend to be used mainly for the transient pressure rather than for the steady state steady pressure. Next, let us look at the tactile sensors. Tactile sensors are basically the touch sensors, and they can be used to sense the touch. Okay. And yes, because of this they can be used in the finger tip of robotic hand and also in the display screen. So let us see what is the principle for these tactile sensors. Okay. So as I said, these are form of pressure sensors, and one form of the tactile sensor uses piezoelectric polyvinylidene fluoride, that is PVDF film basically. So you can see that the PVDF tactile sensors has basically the PVDF film is there, and there is a soft film, and you have the AC input from here, and the output can be taken out from here. Okay. Here in this case the reverse piezoelectric effect is used, okay, and as I already told you, they are used in the fingertips of the robotic hand and also used in the touch screen. So, the two layers of the film are used and are separated by a soft film which transmit vibration. So, basically this is PVDF film, and this also is the PVDF film. Okay. Now, here let us look at the working principle of it. So, the lower PVDF film has an alternating voltage applied to it, and this results in mechanical oscillations of the film, that is because of the reverse piezoelectric effect. Okay. And these oscillations are transmitted to upper film with the help of the soft film. So, the intermediate film transmits this vibration to the upper PVDF film, and as a result the result of the piezoelectric effect, these vibration cause an alternating voltage to be produced across the upper film. Okay. And when pressure is applied here, say by the fingertip, okay, so when the pressure is applied to our PVDF film, upper PVDF film, its vibrations are affected and the output alternating current is changed, and basically that change is the sense that something has pressed the surface. Okay. Next, let us look at the liquid flow. Okay. You see that the liquid flow measurement basically is based on the principle of the change in the pressure basically. Okay. So, the method of measuring Q is based on the measurement of the pressure drop occurring when the fluid flows through a constriction. Now, this constriction could be either you have reduction in the cross section as it is there in the venturi meter, or as it is there in the orifice meter. Okay. So, this is the basic principle that there is going to be reduction or the flow is going to be a constriction. Okay. Now, so for horizontal tube here, as you can see here, say this side, say side A, you have the area of cross section A1, pressure P1 and velocity V1, whereas say side 2, these values are A2, P2 and V2. Okay. Now, this is a horizontal tube here. Okay. So, we can apply the Bernoulli's theorem. So, P1 here P1 by rho g plus B1 square by 2 g is equal to P2 by rho g plus V2 square by 2 g for the two sections, alright. Then we can use the continuity equation, that is A1 V1 is equal to A1 V1 rho is equal to A2 V2 rho, okay. And so, that is for the conservation of mass actually. So, from here this rho gets cancelled. So, I get V1 is equal to this thing, okay. Then I can find out Q as A2 V2 and I can substitute for this V2, okay. I can substitute for this V2, okay, from here. So, I get Q in this form, okay. So, basically you can see that these are the constant parameter area of cross sections at the upstream and downstream side A1 and A2, and here is the pressure drop. So, basically Q is proportional to the square root of the pressure drop. Okay. So, this pressure drop actually, if you could measure this pressure drop, we can find out the Q. So, that is the principle for the liquid flow. Okay. And as I was explaining to you, the orifice plate is also a type of constriction and which can result in the drop of pressure. Okay. So, if in a pipe I have a orifice plate over here, okay, and say upstream side and downstream side I put a tapping from where I can find out the pressure difference, then this arrangement can be used to measure the flow. Okay. So, it is a disc with a central hole placed in the tube and the orifice plate is simply cheap and very widely used. Okay. But again, because there is a constriction here, okay, so it will be difficult or constriction can choke your orifice. So, because of that it does not work well with the slurries. So, if slurries are there, orifice plates cannot work very well on that. Okay. And the accuracy is typically about say 61.5% of the full range and it is non-linear. Why non-linear? Because we have seen the relationship that is here the Q is proportional to square root of P1 minus P2. So, this is a non-linear relationship. So, there is an appreciable pressure loss in the system to which it is connected. Next type of flow measurement device is the turbine flow meter basically, where you have a turbine blade here and the flow takes in this direction and there is a magnetic pickup coil, okay, here. So, it consists of actually the multi bladed rotor that is supported centrally in the pipe along which the flow occur, and the fluid flow results in the rotation of the rotor and the angular velocity being proportional to the flow rate. Okay. The angular velocity of the rotor is going to be proportional to the flow rate, and the rate of revolution of the rotor can be determined using the magnetic pickup. Okay. So, that is there, and the pulses can be counted, and so the number of revolution of the rotor can be determined. So, that way we can measure the flow. Next, let us look at the measurement of the liquid levels. How does the liquid level is measured? Okay. So, one of the basic way could be that we just measure directly the position of the liquid surface, or indirectly by measuring some variable related to the height. That way we can measure the liquid level. Okay. So, the direct method can involve floats as they are used in our water tanks in our houses, and the indirect method can include the monitoring of the weight of the vessel basically. Okay. And how do you monitor the weight, okay, which is a type of force? Then again we can use the load cell. Okay. So, the weight of the liquid you can see that it is Ah rho g, and so this h is proportional to the weight. So, the more the weight, more the height. Okay. So, that is there. So, this is the principle by which we can measure the weight, measure the height. Okay. So, there are indirect method also, there are indirect method that involves the measurement of the pressure at some point in the liquid. Okay. And you know that the pressure is proportional to the height of liquid column basically. Okay. So, we can also have that is a height we can measure by knowing the value of the pressure at that particular point. Then let us look at the float system. Okay. So, here the float system, you can see that there is a water over here and we have a float, and this float could be contacted with a potentiometer basically. Okay. That could be there. So, the displacement of the float causes a lever arm basically to rotate, and so move across a slider in a potentiometer, and the resultant is an output voltage related to the height of liquid. Okay. So, this way we can use the float system to measure the height of liquid. Okay. There could be other form also where the lever causes causing the core in an LVDT to become displaced or stretch or compress a strain gauge element. So, that can also be used. Then there are differential pressure sensors basically. Okay. Differential pressure sensors, it is a liquid measurement based on the measurement of the differential pressure. Okay. So, the differential pressure cell determine the pressure difference between the liquid at the base of the vessel and atmospheric pressure. So, here and say here. Okay. The vessel being open to the atmosphere. So, that way we can find out the differential pressure. Now, let us look at the temperature sensor. Okay. Changes that are commonly used to monitor the temperature or the expansion or contraction of solid, liquid or gases. Okay. With the help of these expansion or contraction of the solid, liquid gases, we can measure the temperature. Okay. And also the change in electrical resistance of conductor and semiconductor, that can also be a way of measuring the temperature, as well as the thermoelectric EMF change also can be used for the measurement of the temperature. So, either of these three ways can be used for the measurement of the temperature. Let us look at the first example, that is the bimetallic strip. Now, in case of bimetallic strip, as you can see that there are two strips with different expansivity. Okay. So, you have the high expansivity material here and the low expansivity material here. So, the both put together, and this is what we call it as the bimetallic strip. Okay. So, there could be a soft iron over here, and say there is a small magnet, and you have the set temperature adjustment, and then you have the electrical connections over here. Okay. So, this device consists of two different metal strips which are bonded together, and these materials have the different coefficient of expansion, and when the temperature changes, the composite strips bend to curve bend into a curved strip, and with the higher coefficient material on the outside of the curve, and this deformation may be used as a measurement of the temperature. Okay. So, the deformation may be used as a temperature controlled switch, and this type of device is basically the bimetallic strip is used in the domestic heating system. Next, let us look at the RTDs, okay, that is the resistance temperature detectors basically. Okay. Here the temperature is detected with the help of change of resistance. Alright. So, the resistance of most metal increases over a limited temperature range in a reasonably linear way with temperature. Okay. And we know this very popular equation which you might have studied in your intermediate classes, okay, that is RT is equal to R0 1 plus alpha T, okay, where alpha is a constant for the metal or temperature coefficient of resistance. Okay. Now, RTDs are a simple resistive element in the form of a coil or wire of such metals as platinum, nickel or nickel copper alloy. Okay. So, here we can see the variation of resistance with temperature for some of the metals, it is shown here. You can see nickel, copper, platinum. So, for a considerable range you can see that for platinum you have almost a linear range, okay, and for copper there is some linear range up to some portion. Similarly, for the nickel also there is some linear range up to some temperature. Okay. So, when the temperature increases, basically the RT increases, and that RT resistance measurement is basically the principle of the resistance temperature detectors. Now, next let us look at the thermistors. So, the thermistors are basically a small piece of material made from mixture of such as metal oxide and of metal oxide such as those of say chromium, cobalt, iron, manganese and nickels, and these oxides are basically semiconductors. Now, they give a large change in resistance per degree change in the temperature. Okay. And again the drawback of these devices are there is a non-linearity in that, and this material can be formed into shapes, say you have bead is there, you have disc, the two terminals, you have the rod, the two terminals like this. Such thermistors have negative temperature coefficient basically, okay, and the changes in resistance per degree change in temperature is considerably larger than that which occur with metals. So, thermistors are rugged and can be very small in size, okay, and these are used with the electronic systems for cars to monitor such variables as air temperature, coolant air temperature. Next, let us look at the thermodiodes. Okay. Thermodiodes again device for the measurement of temperature. Now, in a junction semiconductor diode, when the temperature of doped semiconductor changes, the mobility of their charge carrier changes, okay? And this affect the rate at which electrons and holes diffuse across the p-n junction. Now, when the p-n junction has a potential difference V across it, the current through the junction can be given by the popular equation which you have studied in your electronics course. Okay. Here your T is the temperature on the Kelvin scale, is the charge on an electron, and K and is I0 are the constants. Now, by taking logarithmic equation in terms of the voltage can be obtained here like this, and so for a constant current we have V proportional to temperature in the Kelvin scale, and their response is a linear function of temperature, and the commercially available form is say LM 3911 N. So, this is how commercially they are available. Next, let us look at the thermotransistor. Okay. So, in a thermotransistor, the voltage across the junction between the base and the emitter depend on the temperature and can be used as a measurement of the temperature. Okay. And best example is LM35 which is commercially available, and this sensor can be used in the range of say -40 to 110 degree and gives an output say 10 millivolt per degree centigrade. Then next let us see the thermocouple which is being used for the temperature measurement. Okay. So, for the thermocouple all of you must have studied earlier the basic principle of thermocouple, that if two different metals are joined together a potential difference occurs between the junction. Okay. So, if you have say metal A and metal B, okay, and if there are two junctions, say this one is a reference junction and another is a hot junction. So, if they are placed like this, then you get an EMF, that is the principle of the thermocouple. So, the potential difference depends on the metal used and the temperature of the junctions. Usually one junction is held at 0 degree centigrade, and then to a reasonable extent the following relationship holds actually: E is equal to AT plus BT square, where A and B are constant for the metal concerned, and these are commonly used thermocouples are given in the reference letters here. So, these are the reference letters basically EJK, RST, and these are the materials for these thermocouple pairs. Say chromel for E, basically it is chromel and constant 10, and their range is -200 to 1000 degree centigrade, and their sensitivity is 63 microvolt per degree centigrade. Okay. So, likewise it can be given, and this plot actually says the EMF versus temperature for various these EJK, TRS and all. Now, let us look at the light sensors. Okay. These light sensors are actually the photodiodes, and they are semiconductor junction diode connected in a circuit in reverse bias basically, okay, and thus giving high resistance when light falls on the junction of diode. Extra hole electron pair are produced, the resistance drop and the current rise appreciably. The reverse current is very nearly proportional to the intensity of the light in this case. Then the phototransistors, these phototransistors are they have light sensitive collector base PN junctions basically, and when no incidence light is there, there is very small collector to emitter current. Okay. And when light is incident, a base current is produced that is directly proportional to the light intensity, and this lead to the production of collector current which is a measure of the light intensity. There are these are often available in what is called it as the Darlington arrangement basically. Okay. So, this is the Darlington arrangement in which these are available. Then we have the photoresistors, its resistance depends on the light falling on it basically, okay, and as the name indicate photoresistor, okay, and it decreases linearly as the intensity increases. Okay. Cadmium sulphide photoresistor is most responsive to the light. These are the references. If you want to have further reading, you can refer the Bolton, a very popular book on the mechatronics, electronic systems in mechanical and electrical engineering by Pearson. Thank you.